Hello world, my name is Victor Engelmann, and in this video I will explain flex to you. What is flex? That is a very interesting program which allows you to give it a list of regular expressions and associate with them so-called actions, and then it will generate a program that will read some input stream, and whenever one of these regular expressions matches part of your input stream, then the corresponding action is executed. This sounds a bit like awk, but flex is more flexible because it doesn't it gives you a C code or a C++ code, depending what you tell it what you want, and then you can interact with that in a much more flexible way. So let's just start going into that. So I will just create something like a flexsample.l is a common file type .l. And I will have a main CPP and a makefile. And then I will run my trusty text editor Kate. Okay. Now, in Flex, in your Flex files, you always have these two lines with %%, and these lines subdivide your input file into 3 sections. Up here you have a section where you can set different options. In the second section you define your rules, so that this is where you put your regular expressions and the associated actions. And down here you can just add some additional C or C++ code that will then be put into the resulting file with the generated code. Okay, so let's just start with some simple rules. So I might be looking for the word if I'm writing a programming language. And the associated action, for now I will just do a standard cout if with a space behind it, and maybe do the same thing with a while. Maybe something like print and a read. Then you would normally have some way of dealing with the situation that your file has ended. For example, by saying return 0. Okay. When you turn that into a CPP file, so you can turn that into a CPP file by running flex on it. So with the CPP file here set as the output, and as input I will use the lexa file. Okay. And yeah, then of course I want to compile that CPP file to a object file. And I would do that with G++. Compiling the input file. Okay. I will get a main.o from this CPP file, and then I will get a flexsample.o from flexsample CPP, which will be generated from flexsample.l. And yeah, I will put them together like this. So I will produce a file called flexsample, and as inputs I will use all these object files. Okay, so yeah, let's try compiling this. First I will set the option C++ because I want a C++ code. I won't put anything down here for now. And yeah, since I'm using cout here, I need to include IOStream, and yeah, one of the options that you can use is this percent open brace, percent close brace, which allows you to define some code that you want to have in at the beginning of your file. Okay. Okay, here are my 3 files. You see I'm LFS programming flex. Yeah, let's try make flexsample.cpp, and it has generated that code file. Yeah, let's look into this file a bit. When you look around here, at first it's a bit intimidating, but actually you can make sense of most of it. So yeah, let's see. Look, it decided to include IOStream anyhow, so I didn't even have to do that manually. Yeah, here this is the code that I defined in that percent open brace, percent close brace. These are some tables that define your automata. There's a lot of code here that basically runs that automaton. So this YY state type, for example, YY current state, this stores which state you are currently in. So it's using an automaton internally. And look, here we have the different codes that are executed when the if rule applies. Then this is executed. When the second rule applies, this is executed, and so on. Yeah, something that's very important here is that this YY deckel is So this is the name of the function that is generated. So flex generates a function called yylex, and in the C++ case, it generates that not as a function, it generates that as a method for a class called flexlexa. And when you want to access that from your main CPP, then you just have to include flexlexa.h. That header file is, I think it's installed when you install Flex. And then you can write your main file. And in here you can then instantiate a flexlexa. And then you can give it just some input stream and output stream. So this will read standard in, and you can write with a function or a macro called echo. I haven't used that yet, but if you use that, it will write to this output stream here. Okay. Then in the end, I will delete that lexa again and return 0. And in between you can then just call lylex. As I said, this is what I had shown you here, that you get a function called yylex as a method of a class called flexlexa. Okay, let's see if that compiles. That compiled. That also compiled. Okay, now it's complaining that there is no function called ywrap. Flex gives you a few different ways of dealing with the end of file, and one of them would be calling a function ywrap, and I would normally just disable that. No ywrap. And this time it compiled, because I have this rule here for end of file, and you just don't need ywrap in that case. Okay. Okay. Now I've started flexsample, and it now what I told it to do, it now runs this lexa on this input stream. So it's now waiting for input on standard in, and I could just say if, while, what else did I define? If, while, I don't know, print. So it executed this first rule, writing capital if with a space behind it, then a while and a print. Okay, that's pretty cool. I think I can think of a lot of things you could do with something like that, but I've actually never used it to do anything other than for the first pass of programming languages or other kinds of parsers. So yeah, let's go a bit into that. You might have noticed I put here if, while, print directly behind each other, and that's because I have no way of dealing with white space yet. So let's put some way of dealing with white space. Yeah, a space, a line feed, a carriage return, and a tab stop. If I have them, and actually any number of them, the associated action with that is just to ignore white space. So if I do that, then I can now say if, while, print, oops, with any number of white space in between, and it will still give me this this if, while, print with only one white space in between. Okay. One thing I want to mention here is how does flex really work? I mean, the same part of the input could match multiple of these rules, right? So you could have something like, I don't know, something like while if as a rule, and yeah, if you read a while if, it could then this, I don't know how to explain it. If I would now if I would now input while if, I only get this one while if. Okay, so just because this also matches this if back here, and this while also matches the while in front of here, it doesn't mean that they are also executed. The thing is that flex really chops your input into segments, and each of these segments only apply to one of these rules. You know, and if you already have, if your while has already been part of the match up here, then it will not be part of the match down here again, and this if neither. And the way flex does this, and this is really important to keep in mind, is that if the front of your input matches something, but then it matches something longer, then that longer thing will be the thing that matches. Okay, so it's looking for a longest match, and only when nothing else matches anymore, only then will it take that part of your input, match that rule, and then it will be gone from the input, and then it will start over on the rest of the input. Okay, so after this while if has matched, the while if is taken away and thrown away, and yeah, then these other things just aren't applied anymore. Okay, but that immediately brings us to a very important question, and that is identifiers. Like, for example, when you have variable names. Variable names usually allow you to have characters A to Z, uppercase characters A to Z, 0 to 9, and an underscore. These are typical rules that you can have for variable names, except that you are normally not allowed to have 0 to 9 as the first character, because otherwise because otherwise something like 1, 2, 3, 4 would match your rule for variable names, and of course 1, 2, 3, 4 is a number and not a variable name, right? So yeah, just to avoid that problem, the first thing has to be something that isn't a number normally. Okay, good. So let's say this is a variable name. Or commonly named or commonly called an identifier. Now, what do you do with this identifier? Because, I mean, the word while, for example, also matches this definition, right? So you have a W, which is in this range here, so that W would match this, and H, I, L, and E are all in here. So the word while would also match the identifier rule. And the way you can deal with that in Flex is just by having this rule down at the end of the input. Because Flex, when you have multiple rules that all can apply to the same part of the input, then it will only use the first rule that applies. So if I put this up here, and then it already complains that some of the rules, namely these 4 here, are now impossible to apply, exactly because of that. Because if I write while now, it tells me it's an identifier. But if I put it down here, now it doesn't complain about rules that are not applicable. Now if I input a while, I get a while, right? So, so keep that in mind. The way Flex chooses which rule to apply by a method called first longest match. So, so it always tries to get longer matches, and only when you have one match that cannot be extended to something that still matches. I mean, if I had a variable name like I-foo, for example, that wouldn't be a very uncommon variable name, you know, I as a prefix for an integer and then variable name foo. I only get an identifier, although this if would match the if, right? But there is more input behind that, so I-foo matches this down here, this identifier, but doesn't match the if. But since that is a longer match, this is preferred over this if. Okay, I think that makes sense. Okay, so yeah, then one thing you might want to have just as the last rule, it's not uncommon to have a rule that matches just a single character and any character, so that you can say here lexical error, because yeah, this rule can only apply if you have a character that doesn't fit into any other rule, right? Because if I have an if, for example, I match up here. If I have something, some textual thing, it matches this part here. And a single character. This is the shortest match you can have, and it's really down at the end of the file, so it would also have the least priority. So this can really only apply if something falls through all these other rules, and then it's just a lexical error. It's just a character that doesn't fit with anything. Like while now it says unexpected, first while for the while, lexical error unexpected character for the open parenthesis, identifier is a foo, and then another lexical error for the closing parenthesis. So this is like the emergency rule at the end, to just catch anything that that doesn't match anything above it. Okay, so now let's talk about how we can really use that to get a token stream for our parser. Because right now we are just writing stuff to stand it out. But yeah, in reality we will want to get some information out of this lexa, and yeah, the one way you could do that, I personally like to do it by defining a macro called token x, and then you can change how your lexa deals with your tokens. Like, I mean, I could just for now just say standard cout x. Okay, and now I could say, I could replace all this with token if. Okay, so it still does the same thing, but now we can start doing other things with it. Like I could make something like tokens.h, and in here I could define something like an enum with an if, while, print, read, identifier and number. And yeah, now I could include that. And replace this by just saying return this token. And yeah, maybe I will even put that in a namespace to make this more clear. Okay. Now in here, can also include that. And yeah, the thing now is, if I return this such a token if now, this ends the yylex call. So I could say token tokens token t tok equals reinterpret cast tokens token t. Remember that this function returns an integer, and you can cast integers to enum types. So yeah, let's just say we read the first token, and then we can do something with it. Okay. Yeah, let's try that. Tokens.h. Oops. Come on, tokens. Okay, there we go. So if I put something like while if foo, it now only reads the while, then it returns a token. So then it returns this enum value for while, and out here I capture that and then go into this case where I print this while. Okay, but of course you normally wouldn't only want to get the first token, you want to get every token, right? So yeah, you would just put this in a loop. Yeah, here we return 0 for EOF. I will just make this another token. So, and the EOF token is usually token number 0, that's why I will put it up here. Yeah, and here I will just say if toc equals tokens EOF, then we break. Okay. I think EOF might be not available. Okay, now it works. Okay, remember EOF is not a valid name for a token. Okay, now we get Okay, now we get all the tokens again. But right now we only get the token itself. In reality, you would also want some additional information, of course, you know. You don't only want to have the token number, you also want to know which number is it that you had in your input, or which identifier was it that you had in your input, right? So and Flex also has some support for that. So in your rules you can access the variables yylen, that's the length of your match, and the variable yytext, that's a pointer to the string buffer that holds the text that has matched. So so something that you might want to do is you might want to set some string pointer. So the thing is, after your rule has matched, this pointer to yytext is no longer valid. So like this, I just copy this string to the heap, and then after the rule has matched, it's okay that that this pointer is no longer valid. And I will do the same thing down here when we have the number. But now this pointer only exists inside that rule, and we have no access to that from the outside. When you combine Flex with Bison, you can tell Flex to use some Bison compatibility mode, and then it will do all this stuff automatically. But for now, I will just do it like this. I will just define this as extern string pointer, and then in the main CPP, I will define that. Okay. And now we can use that here. But we need to make sure, I mean, this is a bit hackish, you know. We allocate memory on the on the heap here, and it's not really good style to delete that in a different position than where you've allocated it, but okay. Good. Otherwise we would have a memory leak. Okay. Okay, this looks pretty good. So if this is our source code that we put in our flexer, we get the token while, an identifier token that tells us the identifier was foo, an identifier, an if, an identifier token that tells us the identifier was bar, then a print and an identifier for something, and let's say 1, 2, 3, 4. Now I get a token for a number that tells me the number was 1, 2, 3, 4. So yeah, this is pretty good. So now we get tokens and associated informations out of them. When you're dealing with Bison, then this thing over here will normally be called something like YYLVAL. Okay, this is just a name that is used in the so-called Bison bridge. Now let's talk about a case. Maybe you're trying to write something that needs multiple lexers, like something that has multiple parsers, and each of these parsers is supposed to have its own lexer associated to it. Then of course this will cause a lot of problems because you generate a class named flexlexa and give it this yylex function, and now you're trying to make another lexer, but now it would be it would get the same class name yyflexlexa. And to solve this problem, you can go to the options here and give it the option prefix, and just anything like foo, for example, and this will affect the name of the class. So your class will not be named yyflexlexa anymore. It will now be called fooflexlexa. Fooflexlexa, and yeah, to up here you need to define yyflexlexa as fooflexlexa, so that this flexlexa.h also respects that. Yeah, let's compile this now, and yeah, this now still compiles, and we've changed the class name, and yeah, in your other class name, in your other lexa, you would just use a different prefix, have a different flexlexa, and you could even use both of them in the same source file here, because you could then just say undefine yyflexlexa and redefine it as bar flexlexa, and then you could have two different lexers, one foo flexlexa and one bar flexlexa, link them against both .o files, and then you're good. Okay, so that's how you can deal with multiple lexers in the same code. And yeah, there's a lot of other things that you can do with Flex. It's really a very flexible tool. So just Google for Flex manual, and it's a pretty good manual. There's a lot of things that you can look up here, like multiple input buffers, for example. That's relevant when you want to have something like an include. You know, when you include something in a C or C++ source file, then or also in a header file, then the C preprocessor will just read that file, right? It kind of stops reading this stuff and then reads that file in between. And that's what you would do with multiple input buffers. So you would have something like, if you have something like an include, however you put the file name here, then you could say YY create buffer and switch to that buffer to which no, you wouldn't switch to that buffer, you would push that buffer, right? So the buffer Flex uses a stack of buffers for the different files that you are reading, and in this include rule you could then here there's an example down here. You could fopen that file and then say YY push buffer state, YY create buffer. So this input file is then put into such a buffer object, and that buffer object is put on the stack of buffers. And then what that means is that Flex is now reading that file instead of the file that you've been reading before. And when you have when you're done reading that file, you would then call YY pop buffer to go back to the file that you've been reading before. Okay, I think that makes sense. One more thing I want to mention is that up here in the options you can define parts of regular expressions, like digit might be 0 to 9, and then you can use that down here. This can be useful if you have something that, if you have part of your regular expressions that you need in many places. Okay, so that's something that you can do with these variables. And something that you've just seen here in the manual, if you look at this example, they are looking for the keyword include, and what they are doing here is they have basically a separate second language built into this. So this %x means you have another, basically a second set of rules called incl for this include. And down here you have these incl prefixes in front of the of your rules, and so what this thing does is it looks for the word include, and when it finds this word include, then it goes into this other set of rules, and in here it looks for something for something that's not white space. So for example, a file name, it first skips white space and then it looks for something that doesn't contain white space, and when it finds that, then it is stored in YY text, and that's used as file name here. Okay, and this begin incl means once we've read this include, we start looking for some file name. When we found it, we open that file, push the buffer, and when we are done, we go back to the initial set of rules. Okay, so so this is like a separate set of rules, and yeah, sometimes you just need to to do something like that. Okay, so yeah, the way you can do that is in here in the options you say %x, and then you give names to your sections, and then you can put your rules into different sections, and they can even be part of the same of multiple sections. And if you want it to be part of all sections, you can use this star. Here with a comma you can put it into into multiple sections, and if you don't have any prefix, then it's only valid in this initial section, which is an implicit one. That's the default section. Okay, that's the one that they go back to here. Okay, and then you can just jump around between these sections with this begin macro. But okay, yeah. That was some advanced stuff. So yeah, if that was too fast now, just go into the manual. They have examples and they explain everything pretty good. So yeah, I don't want to go too deep into that. I just wanted to mention that this is something that you might have to deal with. Like, for example, something like this is, for example, done in PHP, where you would normally just pass everything to the next layer. You know, just everything is echoed to the resulting file, except when you find this open ?PHP, then they go into some other mode, and in that other mode they handle stuff, and when in that other mode, so there you would have something like if then else and while and stuff like that, and when you find the text ?close, then you go back to the initial stuff. So this means that everything is just echoed, except when you find this start of a PHP section, then you start dealing with all the programmable stuff, and at the end of your PHP section you go back to the mode where you just output your stuff. You know, in a PHP file you would normally have something like HTML head, and this would just be passed to the output by this, and only when you have your PHP stuff, then you can have your programmable things I don't know, something like this. Okay, so so again, this rule would just print out this stuff to the output that goes to the browser, and then here you say, okay, here I have a semantic section where I then have my rules for if and while and so on. Okay, so I think this is really enough for today. We've covered a lot of stuff. I hope I could give you a really good overview over what Flex can do and how you can use that as part of your lexical analysis. And yeah, in the next video we will start talking about context-free grammars, which are then the basis of Bison and the syntactic analysis part of a parser or like a programming language compiler. And yeah, so if you're interested in compilers, definitely don't miss that video, because as I said, this is really the basis of Bison, which is a very useful tool for generating parsers like programming language compilers. So absolutely don't miss that. And yeah, if you like this video, like it, share it, subscribe, and see you next time.